going to meet R at some point. So this is a very intuitive thing, but such a simple thing, it is really based on Euclid's parallel axiom. So what Euclid's parallel axiom says, that if you have a line which is intersecting two other lines such that on some side the sum of internal angles is going to be less than two right angles. So if you have such a thing, then these two lines, if they are extended long enough, will go and meet somewhere. So which is really saying the same thing, right? Because what is parallel?
And what happens after he drops Euclid's axiom? He comes up with something like this. So for Riemann, plane meant something else because he started with different axioms. And on his plane, whatever line you take, wherever they are, they always tend to meet. So they are not really lines or planes in the same sense of Euclid, but then they started with different axioms. So the point that I want to emphasize on is, you start with different rules and you end up having different derived rules. So the game becomes completely different if the weapons are different. Okay, however, before going into axiom of choice, I have a confession to make, which is I really have no clue okay, I shouldn't say I have no clue, but I don't have much clue, because what I work on has really got nothing to do with axiomatic set theory, other than the fact that in any field of mathematics, of course, you have to use logic in some way, but other than that, this is not something I work on or I know a lot about. So why I chose this topic? Because when I was about your age, like when I was finishing my 12th, then so one teacher of mine gave me this book and I was like really inspired by this book. I mean, it won't be wrong if I say that one of the reasons why I took up mathematics was I got this book when I had just finished 12th standard. So I just thought that since you are also in the same age group, it might be fun to go back to this book, and maybe some of you will actually go back and take this book and try to read and I don't know, have some fun with it. So that is the confession. So now let's go into axiom of choice. Let's start with a story, one fiction. So there was this prince in a land of immortals. So the prince was not going to die. That is one important thing. Who around the year 1904 went a bit crazy about marriage. So what does it mean to say he went crazy about marriage? So he wanted to get married to not one, not two, but as many countries as there are, not in just his own planet, but the planet in the next orbit, and the next orbit, and the next, and even the ones out of his galaxy and so on. So basically, point is there were infinitely many countries from which he wanted to choose his bride. However, he didn't want to make it too big celebration, so he asked for just one bride from each such country. So basically, what it means, it's really like he had these infinitely many boxes and he wanted to choose one thing from each. So the question was how? See, if the prince was going to die at some point, then cool, of course he won't get enough time to get married to so many women, and if there were finitely many planets, then also this is not such a difficult thing to do. I'm sure a lot of princes do that, but unfortunately the number of planets were not finite. So how does an immortal prince make sure that he really can have his brides, one from each of the infinitely many planets that he wishes to explore? Because see, the point here is infinity, because we can't really say anything about infinity, right? Sorry. So what the prince did, he called this court logician called Zarmelo. Zarmelo in fact solved this problem, but he did something more. He gave the prince a set of 9 axioms. one of which solved this problem, axiom of choice that we are going to talk about. But there were other 8 axioms which were not used by the prince, but it was later used by mathematicians. So what is really axiom of choice? Axiom of choice is something that allows the prince to choose one bride from infinitely many countries. So if you formally write that, it says that you have this infinitely many or whatever, even finitely many of index set I. What it really says that, say, take I as one. Try to prove it mathematically by yourself using induction. That you don't really need axiom of choice for this, it's easy. But for infinite, what can we say? That's why the axiom, that's why the rule. Okay, so I want to mention this other equivalent statement of axiom of choice, which is also widely used in mathematics. So what it says that if you are given a collection of non-empty sets called the collection C, then there exists a function from C into those sets which are elements of C with this property that if you choose one set from that collection of sets, then f of A is inside that set, that very set. Now it's not very difficult to see that these two things are actually equivalent. So let's assume 1, we want to prove 2. So we know 1 and we are given C, a non-empty family of sets, non-empty sets. So let's write C as this. This makes sense, right? We are just rewriting it as in the most obvious way. Now we want to match it with 1. So instead of A, we just rename the sets as XA. So now the index set is C itself. So how do we define the function f? Naturally as small xa, which is inside capital XA. And why 2 implies 1? So now we know 2 and we are given that family. So call that family C. Now we need some small xi's. So what is the obvious choice? F of capital Xi, which is inside capital Xi. See, these are, when you come to think of it, these are really very intuitive, very obvious things to say. But actually to write them in the language of mathematics is what brings in the challenge. So this f is naturally called the choice function because you can see that this function f only is really allowing him to choose from those sets. So with the court logician's help, the prince got married and that's the end of that story. So let's go into another story, which comes as a funny application of axiom of choice. Suppose a professor has infinitely many students in his class and each student has awesome memory, very good memory. So he took a very tough class test. So the students are not sure how they scored. So what the professor did, he gave marks to each student and he wrote down those marks as an infinite sequence. So this S1 is the mark for student 1, S2 for student 2 and so on. So he then makes a deal with his students that next day he will call student K. So starting from K equals to 1, he will call student K to his office and show him this sequence, the grade sequence that he wrote down, but he will hide student K's marks, that is he will hide SK. Now student K has to guess what SK is and immediately go home, not talking to anyone else after that, and then the next student is called in. So after the whole process, if all but finitely many students can guess their own grades correctly, then he will give full marks to all. See, there are infinitely many students, right? So if only just finitely many of them say it wrong, he is ready to forgive. So assuming that the students are allowed to meet beforehand and find some strategy, the question is whether they can do something to win their case. So what they do, they write down every possible such infinite sequence. See, I said that they have very good memory, right? So when I said they have very good memory, I meant that they can remember infinitely many things. So they write down all such infinite sequence where the entries are coming from integers between 0 and 100. what they do, they write down these sequence in small sheets of paper. Okay, not very small because it's an infinite sequence. They write them in big sheets of paper, and now they sort those pieces of paper into shoe boxes. So there are infinitely many students, so they have infinitely many shoes, so they have infinitely many shoe boxes. What they do, they sort them with a certain rule. So two infinite sequences will be put in the same box if and only if so they will go into the same box if and only if they differ by only finitely many terms. So what it means? Say you have a sequence like this, which keeps increasing 1, 2, 3, 4, 5, 6, so on, and you have another sequence which is all 0. So they differ from each other in infinitely many places, right? So they will be put in different boxes. Whereas if you have another sequence, say 1, 0, 0, 1, 1, and then rest of them are 0. So this differs from this only 3 places. Therefore, they will be put in the same box. So this actually gives a nice relation so that you can really sort these sheets of paper in this way. Now we use axiom of choice. So what does axiom of choice allow you to do? It allows you to choose one representative sequence from each such box. Now you have infinitely many boxes and each contains many sequences. You can choose one from each such box by axiom of choice. And since they had very good memory, they can completely memorize these representative sequences, what the entries are, and also from which box the representative is chosen from. Now next day they go to the professor's office. Starting with k equals to 1, student k sees an infinite sequence with the kth term omitted. But there has to be at least one representative from which this sequence differs in finitely many places. There has to be one such. But he remembers all the representatives. So he knows which box this is chosen from. Let's call that box B, and that representative sequence, let's call it B1, B2, B3. This sequence of course differs from this in only finitely many places. So student K guesses that SK is BK and he leaves, doesn't talk to anyone. And the next student comes in and again he knows what's happening, so he guesses that SK plus 1 is BK plus 1. But B1, B2, B3 differs from S1, S2, S3 in only finitely many places. So which makes it possible for the students to guess it correctly, all but finitely many, and they win their case. So the point of mentioning this example, other than the fact that it's always pleasant to win over teachers, that students winning over teachers, the point is axiom of choice really has got something to do with infinity. See, all these things are happening because there are infinitely many things. So that's one point I'll just like to mention, that there's something happening about infinity behind all this. Okay, so now something less fictional. Incidentally, this is one application that Halmos also mentions in his naive set theory book right after he states axiom of choice. So what it says, that any infinite set, again infinite, that is important, any infinite set X has a subset Y which is really like the set of natural numbers. So again what it means, that you have an infinite set and so on. This is X. Uh-oh. So maybe this like. Okay, if I write that side, will you? This is fine? Okay. Okay, so see, intuitively this is clear. Why this is clear? Because it's an infinite set. So in particular, there is at least one element in it. Let's pick this element, call it x0. Now, if we omit this element from x is infinite set, so x minus x0 still is non-empty. So I can choose another element x1. Now I omit this one also and choose another one x2 and keep doing this for infinitely many times. So I really have this subset of x which is exactly like the natural numbers. So you just defined v0 as x0, v1 and as x1 and so on. You're asking something? So again, intuitively this is clear, but what it really means that we can go on for infinitely, we can do this for infinite times. Again, what can we really say about infinity? So I'll just give a formal proof where you can really see how axiom of choice is being used in these kind of things. So you remember that collection C and the choice function, right? So for us, C is going to be the power set of X minus the empty set, because in case you didn't notice, for axiom of choice, all these boxes have to be non-empty. Otherwise, it doesn't make sense picking one element from them. So let's call C as this, and let's take F as the choice function on C. Now, call F as set of all finite subsets of X. So in particular, empty set is here. And I want to define a function, not I, that's what Helmholtz did. Define a function from F to F given by GA as A union one more element. So what it really says? See, first of all, A coming from F is a finite set. X is infinite, A is finite. So X minus A is non-empty, infinite, and in particular it's non-empty. So it is really in the domain of F. So it makes sense talking about F of X minus A. Moreover, by the property of choice function, we know that F of X minus A has to belong to X minus A, right? So F of X minus A belongs to X minus A. That was the whole point of choice function, which means that F of X minus A doesn't belong to A. So what this really says is, you take G of a set A and it gives you back that set A and another point outside A. This is what G is. Okay, so now I want to define so I want a bijection called V. So I define my V like this. First V0 I define as F of the whole set. Then I take one singleton set, that is one finite set V0, and I see what is G of this finite set. So where should I move that side? So what is G of this set V0? It is really V0 itself and one more element which is not V0, right? So you maybe it's too much glare, no? So call this V0 and one more element. What is that element? F of x minus singleton set V0. So I am of course tempted to call this V1. So now what is G of, okay, so what is this? This is really the set V0 and V1, union of 2 points. Now what is G of this set? That will be these 2 points and another point which is not equal to any of these. So that will be a set of 3 points. So it's V0, V1 and f of x minus V0, V1, whom I want to call as V2. So you can see that this function g, it's taking 1 point V0, taking it to 2 points V0, V1, then taking 2 points V0, V1 to 3 points V0, V1, V2. So it is really like the intuitive thing that we started talking about, right, that x0, x1, something like that. Now there is something called recursion theorem which allows you to name these sets as something formally. So what recursion theorem does, it allows you to have a function R from set of natural numbers into this finite subsets where R0 is empty set, R1 is this set V0 which has just one element, R2 as V0, V1 having 2 elements and so on. So okay, I won't state recursion theorem here, you can just go back and find the book and take a look. That proof is also quite interesting. Okay, so now of course I want to define my function v as v of n being f of x minus v0, v1 up to vn minus 1. Just note one thing, that these Rn's are being contained in one another. So R0 is inside R1, is inside R2 and so on. Now if I define my Vn like this, then what is this really? What is this set V0 up to Vn minus 1? What is it called? Rn. So it is really f of x minus Rn. But we know that f of x minus Rn is inside x minus Rn, which means it doesn't belong to Rn. On the other hand, f of x minus Rn is inside R of n plus 1, because the way we are choosing these, what will be R of n plus 1? V0, V1, V2 up to Vn. So this element is really in here, Rn plus 1 minus Rn. So now going back to the picture which is not there, going back to the picture, see that is V0. So the red thing is R1, the blue thing is R2, the green thing is R3, so it's like increasing sets. V0 is inside R1, V1 is inside R2 but not in R1, V2 is inside R3 but not inside R2, and so on. So you can really see that for different m and n, Vm and Vn cannot be same, they are just in different sets, right? So that proves what? That V is a 1-1 function, is an injective function, right? For different m and n, the value of Vm and Vn will be different. So V is an injective function. Now you take Y to be the range of V, and that of course gives you your required subset, proving the proposition. Now this proposition has a very nice corollary. It says that it really gives a definition of infinity, sort of. It says that a set X is infinite if and only if it has a proper subset with which it is bijective. So see, if X was finite, then any proper subset will have less number of elements, right? And we know that if two finite sets are bijective, then they have the same number of elements. So for finite thing this cannot happen. So this is essentially something about infinity. So can any of you give an example of an infinite set which has a bijection with its proper subset? Let's take set of natural numbers, 0, 1, 2, 3, etc. Rational numbers and integers, but that bijection is kind of difficult to construct, no? That rainfall method, yeah, famous. But is there anything more simple? Right, even numbers and integers. So from n going to 2n, that gives a bijection, right? It's 1, 1 on 2, and even numbers are of course proper subset of set of integers. There is another one where n goes to n plus 1, so everything is shifted by 1. Right, that is another 1-1 function. So why I mentioned that function, because the proof of this will use something like that. So we'll define this function h on x, which takes v0 to v1, v1 to v2, v2 to v3, and so on, and everything which is not in range of v will be fixed, it will go to itself. So using the fact that V is a bijection, one can easily prove that this function h is also a 1-1 function. Why it goes to a proper subset? Because it doesn't contain V0, the range, nothing goes to V0. So that sort of proves this corollary. Incidentally, this notion of infinity is actually same as something that another mathematician called Dedekind's notions of infinity. Parmesh, how much time do I have? So now this axiom of choice is not really used as it is in mathematics. There are some equivalent statements which are used. So something which I find really interesting is that in the statement of axiom of choice there is nothing about ordering, that one element is bigger than another, nothing like that. But the equivalent statement is a lot about ordering. So there is this one equivalent statement I like to mention, it's called well ordering principle. It says any set X can be well ordered, but what does that mean? So well order means a nice order on a set such that if you take any non-empty subset of that set, it will have a smallest element. So For example, if I take this n cross n, and if I put the natural partial order on it, so what do I mean by natural partial order is AB will be less than xy if and only if A is less than x and B is less than y. So this you can just try by yourself, that 1 comma 1 is the smallest element of the whole set n cross n with this ordering, whereas if you take this subset all AB in n cross n such that AB is not equal to 1 1, which means that either A or B is not 1. You take that set and you can prove that that really doesn't have a smallest element, which shows that this particular order on n cross n is not a well order. On the other hand, if you put the dictionary order on n cross n, that gives a well order. So maybe you can try to think how to make the set of real numbers well ordered. What order can you put on the set of real numbers that makes it well ordered? Because the natural order obviously doesn't, right? Because it goes to minus infinity. Already the whole set doesn't have a smallest element by the normal order. So maybe you can think about it. So this well ordering principle is equivalent to axiom of choice, and one side is easy to see. If you assume well ordering principle, then if you have this family of sets xi, non-empty sets, you take the union of all those and well order that set. Now consider xi as subset of this big set and choose the smallest element from each xi as the small xi. So well ordering principle gives you axiom of choice. The other side is much more technical. This is another crazy application of which I won't give the proof, but it's just so crazy that I thought I should mention it. One application of axiom of choice is that given a solid ball in 3D, you can break it mathematically into finitely many pieces and then put them back together to make two of the same ball, which is very counterintuitive, right? But then infinity is often counterintuitive, and that's why it's a lot of fun. So there are mathematicians who are really not very fond of this axiomatic approach. For example, Lakatos, he was like completely dead against this axiomatic approach, and he said that all theorems are wrong. They are just waiting for some counterexample to be found. I mean, he didn't exactly say this, but that was the mood. But in spite of all this criticism, axioms, in particular axiom of choice, which is my favorite, remains a fun thing to play around. Thank you.
Any questions, comments? If there are no questions, let us thank Madhushree once again for her excellent talk.